Welcome to the third lecture on important cuts. In this lecture, we will see our first application of important cuts in designing FPT algorithms. So let's just recall the definition. If you recall correctly, a minimal XY cut delta R is important if there is no XY cut delta R prime with R subset of R proper subset of R prime, and the number of edges between this delta R prime is at most delta R. These are called important cuts. And if you have R prime that R prime that so let's fix a terminology, okay, just to help ourselves. So suppose R is not an important cut, then we know there exists R prime and XY cut such that R is a proper subset of R prime and delta R prime is this. We will call R prime we'll say R prime dominates R. Okay, that's it. So we'll just use this terminology for which will be very helpful. And what we saw last time that, so this is the fact we learned, number of important XY cuts of size at most k is at most 4 power k, and we can enumerate them in time big O of k to the power big O of 1 n plus n. Okay, that's it. Right? So we saw that algorithm in this fashion. Now we are going to see the first application of this enumeration algorithm. Okay, and so the first problem we are going to talk about is multi-way cut. So what is a multi-way cut? A multi-way cut of a set of terminals T is a set S of edges such that each component of G minus S contains at most one vertex of T. So ST cut is like you want to delete minimum number of edges so that S and T are in different component. But now we do not have one terminal, okay, we have set of terminals, and our objective is to delete at most k edges so that every terminal is in single component. It means we have been able to disconnect path between every pair Ti, Tj in T, right? So for example, look at this example. Now, if you delete all these red edges, right, then each of these terminal are in their own component. Or in other words, there are no two vertices in my terminal set T such that there is a path between them after we had deleted the set S. Okay. So what is a multi-way cut problem is? A multi-way cut problem is you are given a graph G, a set T of terminals, an integer k, and our objective is to check whether there exists a set S of at most k, a multi-way cut S of at most k edges. And what is a multi-way cut? A set of edges whose deletion results in every terminal being in a single component. Okay, or every component containing at most one terminal. So this is definitely polynomial time for kernel T equal to, but it is actually NP hard even if you had just 3 terminal and you wanted to delete minimum number of edges, then this problem is known to be NP hard, and it is known by paper by Dalhaus from 1994 itself. Okay, what does that implies? That implies that right? What does this implies? That this NP hardness reduction, that you cannot have an algorithm of running time even n to the power f of terminal, because this will imply p equal to n, right? So we do not hope to have an, so number of terminal is not an important parameter for this problem in general. So the parameter which we will use is the solution size, number of edges that we need to delete, such that these terminals get separated from each other. Clearly, it is trivial to solve this problem in polynomial time for every fixed k. You try all possible k size subset and check whether each terminal belongs to, like, or each component contains at most one terminal, and this can be done in time n to the power big of k, right? Like you try m choose k number of edges and then you do in this. So this will lead to n to the power big of k. But what we are going to show to you that multi-way cut actually can be solved in time 4 to the power k, k to the power q, vj plus ej. Okay, we will start with giving you an algorithm which has this running time, but we will first analyze this slightly easily and then refine our analysis to achieve this kind of running time. Okay, I hope this is clear. So just you can pause for a few seconds at this point of time and phrase these definitions properly and then move into the algorithm. Okay. So let's consider the intuition. Suppose T is a T and a subset of the solution S is a T minus R. Look, what is the property that, look at S. If it is going to delete, if you are going to delete G minus S, then every terminal is in every terminal is in its own component. Then there will exist some subset of edges whose deletion will disconnect T from everybody else, right? In particular, the whole set S itself does this job. So there could be a minimal subset of S which does the job of reducing T from every other term. Okay, and so a subset of the solution S is T minus T. But there are many such cuts. I mean, if you just wanted to disconnect, we know that we know that the number of min cuts or minimal cuts between T and T minus T could be as many as n to the power big of k. So an algorithm where we would like to enumerate all minimal cuts, delete it and then try to disconnect everybody else will not lead to a good algorithm, because that could just become n to the power big of k square. So that's not good, right? We know that my optimum solution contains a minimum cut between T and T minus T. So a natural algorithm will be enumerate a minimal cut between T and T minus H of size at most k, delete this, and in the recursively try to disconnect every other, because after this you know that maybe some set of components, some set of terminals have gone into component, some set of terminals still need to be separated. So you pick one such terminal, try to separate it from the other, you do this, and every time you know that you are going to incur at least cost of 1. So this branching tree is going to be at most k, but the branching depth is going to be n to the power big of k, because you are enumerating all minimal cuts. So there are many such. So this is a natural algorithm, but this does not work because number of minimal cuts, as we have seen, could be as bad as n to the power big of k. So now, rather than doing this, we ask ourselves, what happens if we enumerate T minus T important cuts, because we know that they are only 4 to the power k. Okay, so naturally at this point of time, after developing all this, can we ask ourselves, is it possible that there exists a multi-way cut S of size at most k such that S contains an S T and T minus T important cut of size at most k, right? So we know that a minimal cut, right? A minimal T minus T cut is contained inside S. That's okay. But now I am saying that, look, but that's not useful because there are too many of them. I'm saying, can I find a solution S to my problem which has a property that if I look at t minus t solution inside this is not any minimal cut, but this is an important cut. Because if we have this, then we know that we can enumerate each of these cuts, delete the solution, and in the remaining, try to separate those pair of terminals which are not yet separated. We know that every time we have to pay something, so the depth will decrease by 1 each time, and since the branching factor is upper bounded by 4 to the power k, this will lead to a 4 to the power k square algorithm, but still this will be an FPT algorithm. So that's a goal. So our main objective will be is to show whether such a statement is true, and in fact what we will be able to show that actually such a statement is true, and that is the crux of any cut kind of algorithm, that we are trying to show that look, we can separate one guy from everybody else, and there are some there are too many minimal cuts, but there are a small number of cuts which we will call important cuts, which is good enough for us to enumerate. We do not need to enumerate all of these cuts, because for any minimal cut, if you look at an important cut that dominates it, that does the same job as this minimal cut will do. And that is the crux of this lemma, and these kind of lemmas are called a pushing lemma, and this is what the intuition is trying to do, that a cut farther from t and closer to t minus t seems to be more useful than any minimal cut, and this is the intuition which is, which is encapsulated in the pushing lemma. Like we can push a solution to one of the important cut, because what is the property of important cut is like, look at this important cut, I cannot push this further without violating either the solution constraint, the size of the solution constraint, or the fact that R is not contained inside this. Okay, so this is what we are going to show, that basically we are going to show to this pushing lemma has a solution S that contains an important t minus 2 cut. This is it. Proof, before we go to proof, here it is. The proof is very simple, So you fix any S, okay, and you fix, okay, let R be the set of vertices reachable from G minus S for a solution S. What is R? R is a set of vertices which is reachable from T, right? So these are the vertices which I can reach. So this is my first R. So notice that delta R, which is a subset of S, separates T from T minus T. Okay, this we know. There are two cases. This itself is an important cut. Then we are done. S is that particular solution which has this property. Okay. Otherwise, if delta R is not an important cut, then there exists some R prime so look at this blue. So the red edges are, okay. So let me use green color. So this is the edges. These are the edges of R, but R I know is not an important cut. So what I'm going to do, I'm going to let R prime is T minus T important cut, okay, R prime, okay. And what is the property of this? So the number of blue edges is less than the red edges, which is encapsulated by the delta R prime is at most delta R. So now I'm going to make you a new solution. What I'm going to make a solution, I said, okay, I'm going to make a new solution S prime. From S, I'm going to remove all the red edges, the edges which were incident to R, right, delta R, and from there I'm going to add delta R prime. Now, look, I deleted first delta R and then I added delta R prime. The size of delta R prime is at most delta R prime, which implies that the size wise S prime is at most F, which is at most K, so which is great. But now we have to show that S prime is also a multi-way cut, meaning there is no path between Ti and Tj for any set of pair of terminals in T. First thing first. Okay. First notice there cannot be a path from T and another, there cannot be a path between T to some T minus T, some U or V. Why? Because r prime, delta r prime is an important t minus t cut. So you are still separating this. So the only region you could, S prime may not be a solution, S prime may not be a solution, because in G minus S prime, what happens? Because in G minus S prime, there is a path between U and V where U and V belongs to T minus T, right? Okay. But I know that there was no path before. So how did suddenly I get a path from U and V? Well, the reason you can get a path from U and V is because this path U and V must be containing one of the red edges. Okay? Must be containing a red edges. Okay? But now notice, if there's a red edges, then you must be coming inside, because look, to use this red edges, you must be coming inside R and then going back to V. Okay? Fine. But then what implies? What was the property of the set R? The property of the set R that every vertex was reachable from T, which implies that I can reach T to this vertices, and from there I could go to U. But that's a contradiction, right? Because look, what did I do? So there's a path from U to V. Since this has to use a red edge, otherwise there cannot be. If it uses a red edge, one of the red edge, there is a vertex here which is inside R. Now you know that every vertex is reachable from, so you come to T to X, and from T to this vertex X to A, there is a path from T to U. But you told me that T cannot reach any vertex in T minus T because R prime was T minus T separated. That's a contradiction. So what are we able to show? It's a very simple pushing lemma which tells us that there exists a solution S which contains an important cut between T and T minus T. And once you have shown this lemma, your algorithm is more or less done. Okay. So here is an algorithm. Okay, algorithm. If every vertex of 2 is a different component, then we are done. Otherwise, you choose a vertex T in T. Okay. You choose a vertex T in T, right? That is not separated from every T minus T. Means there is some vertex that is a path. So you branch on a choice of importance T minus T cut S of size at most K, right? You set G minus S and you drop K by K minus S and you go to 1. So what is a branching step? Every time you branch into 4 to the power K directions. And every time, why are you branching? You're branching because you want to separate T from something, right? So you at least need one edge to separate T from T minus T, because there's at least one path, which implies that in each branch, K drops by 1. So the branching depth of this tree is upper bounded by K. So the total number of is like 4 to the power K square. So what did we get? So this tells us that the algorithm has running time 4 to the power K square n to the power big O of 1, or in fact this is like. So what is an algorithm? You rather than enumerating minimal cuts, you pick a vertex T which still needs to be separated, enumerate all minimal cuts, you are guaranteed that there exists an optimum solution containing one of the important cuts, you find this you branches through this important cuts, and you delete this set S, and then in the remaining you try to cut whatever needs to be cut, right? And you know that because of my pushing lemma, you know that there is one branch where you are making a correct choices, and hence this will lead to an algorithm. And now each branching factor is like 4 to the power K, because you're branching in 4 to the power K direction. The depth of this branching is K. So the total number of nodes in this branching tree is upper bounded by 4 to the power K square. So that automatically bounds the running time by 4 to the power K square poly. Okay, or n to the power big O of 1 if you do not want to bother. But we promise that we will give you an algorithm whose running time is actually 4 to the power K and some dependence on poly K n plus n This is too far away. So for that we need a better analysis. Okay. Let's see why this implies. If S is a set of all important XY cuts, okay, we have seen at most 4 to the power k important cuts of size at most k. We'll give you a better bound actually. If S is a set of all important XY cuts, all important, no size restriction, then what we know? What does this say? Look at S in curly S, or the set of all important separator. 4 to the power minus S is at most S. But you may ask, why do I say this is a much more refined bound? Well, look at all important cuts of size at least k. Okay, all important cuts. So let's call this Sk. Look, this is like, so 1 to the power 4 to the power k is smaller than 1 to the power 4 to the power k minus 1. So I can come up with a lower bound, right? This is less than equal to number of important cuts of size at most k times 1 to the power 4 to the power k. Right? This is it. So that implies that number of important cuts of size at most k is upper bounded by 4 to the power k. So this is why I'm going to call to you that this is a refined bound. What we are saying that number of, if you sum them, if you look at the contributions of 1 by 4 to the power important cuts, as the size increases, their contribution to this space of important cuts decreases in with respect to this measure. And this is what we are going to prove. Okay. In fact, what we will show is that number of like 4 to the power minus S, where S is belonging to important separator, is 2 to the power minus lambda, where lambda is the minimum XY cut size. And the way we will show this is by induction, and induction will be on slightly different object. Let me show you on what. So given a graph G, X and Y, right? So induction is going to be a measure where it is going to be number of edges in my graph minus number of edges in the graph induced on X. Right? So this is what my measure is going to be. Okay. So suppose I denote number of edges by M and number of edges in the graph induced on X, okay, to be let's say Q, okay, then my measure is going to be M is going to be M minus Q. So my induction hypothesis is when let's say that M minus Q is 0. What is the meaning of that M minus Q is 0? So here you have an X and here it is Y, right? And there is no edges here, right? That is what it means, that the number of edges is 0, right? So look at the total number of edges. If I delete the number of edges which are here, they are 0. It means there is no edges between X and Y. In this case, what is the lambda for XY cut is also 0. Then in this case, what is my left hand side? My left hand, so in this case, there is a unique important cut, unique important cut, and that has size empty set. So for this is, I'm trying to show for the, this is for base case, okay? Okay, this is base case. So it means what is the left hand side will be 1 to the power 4 to the power 0, and what is the left hand side is like 1 by 2 to the power lambda, which is equal to 1 by 2 to the power 0. So both are 1. So this is fine. Okay. Okay. Let's add an extra page. Okay. So now you recall, right? So now you recall the way every important cut, what we knew about every important cut. Every important cut had the property is the following. So suppose this is my X and this is my y. Every important cut, suppose this has R. What is the property? That they contained the following object, right? This was R max. And how did we counted important cuts? We said, hey, look at all the edges going across, okay? And let's say this edge, and let's call this U and V. So we had two cases. So suppose this is my S, all important cuts between X and Y, okay? So either UB belongs to S, let's call S1, or UB does not belong to S, okay? UB, right? UB does not belong to my S, or UB does not belong to S. This is called S2. So we'll count each of them. So now let's see what happens in the first case. Well, in the first case, when you do not, so here is your graph, this is your X, this is your R max, and here it is your UV. You have thrown this out, and this is your Y. Now notice we have already shown in our branching that every important cut of G minus UB is also an important cut of G, like every important cut of G that contains UB is also an important cut of G minus UB. So what are we going to do? We are going to get all the important cuts of G minus UB and add +1 for UB. So now what are we going to get? So what are we need to bound then? Then we need to bound S belonging to S1, 1 to the power 4 to the power mod S plus 1. This is what we have to do. Now notice what happens to our, so this is a sum we have to upper bound, okay? S in S1, 4 to the power minus H. Now, which is equal to 1 by 4 S in S1, 4 to the power minus 6. Now notice what happens. First of all, in G minus UB, okay, what is this? M drops by M1, and the Q, the edge induced graph on X, Q remains Q. So the measure mu minus mu prime is M minus M minus Q minus M minus U minus Q, right? And so this is going to be 1. So measure drops by 1. So we can apply induction hypothesis here, okay? So we can apply induction hypothesis here. Induction hypothesis here, okay? So we can apply induction hypothesis here, but now we also have to find what is the lambda for X comma Y in G minus UV. Well, lambda drops by exactly 1. It cannot drop by 2, otherwise then you take that, add this edge, and then you are done. So by induction hypothesis, what this number will be? What this number will be is 1 by 4 summation S in S1, 4 to the power minus S, which is less than equal to 1 by 4, which is less than equal to 1 by 4 times 1 by 2 to the power lambda minus 1, and which is equal to 2 to the power minus lambda divided by 2, right? So this is exactly what you are going to get here, right? this, right? You are able to bound by this, which is like 2 to the power minus, because like this is what we have in this, but this is upper bounded by number of all cuts, important cuts in G minus UV, which contains this, and that is what is bounded by 2 to the power minus lambda minus 1 by 4, and that's what you get 2 to the power minus lambda by 2. Okay. Look at the other direction. Other direction, what happens? You decide that, well, UV is not in this, then what you are looking for is that, okay, in the second case, I am looking for all important cuts between this and Y. But now what happens to this? Now notice M remains M, but number of edges Q becomes, so mu drops again by 1 because it is M minus Q minus M minus Q plus 1, right? So mu drops by 1, and hence what we can say for these things, and look in this case what happens, right? In this case what happens? In this case, because this was an R max, the moment you add V to this, lambda, right, increases by 1. Mu drops by 1, but lambda increases by 1 too. So now for S in S2, all we can say, okay, all we can say that 1 by 4 to the power mod S, okay, 4 to the power mod S is less than equal to 1 over 2 to the power minus lambda plus 1, which is 2 to the power minus lambda divided by 2. Okay. So in both sides you are able to bound by 2 to the power minus lambda by 2, 2 to the power minus lambda 2. So you are able to bound the whole thing by 2 to the power minus lambda. Okay. So this is a refined bound we are able to achieve. Now how are we going to use this refined bound for our algorithms? Let's see that. Okay. Okay. So now let's look at the search tree for multi-way cut algorithm. We are going to show that it has 4 to the power k leaves. Okay. Let Lk be the maximum number of leaves with the parameter k. Okay. We are going to prove Lk by induction. So how does algorithm works? You have t minus t. You enumerate important cuts, and then you enumerate important cuts, and then you recursively solve the problem. How many important cuts? Like, so that is what. So this algorithm is going to be, how many number of leaves going to be? So parameter drops in each of these branches. So by induction hypothesis, let's see. So by S in Sk, so the total number of leaves in this is the leaves here plus leaves here plus leaves here plus leaves here, which is summation S in Sk 4 to the power k minus s, right? Because that is so many branches, right? For each S in Sk, the important cuts, it drops by k minus s, and so for this by induction hypothesis, number of leaves is upper bounded by 4 to the power k minus s, the parameter. So the total sum is 4 to the power k minus s, S in Sk, which is 4 to the power k if you take out S in Sk, and this you know is upper bounded by 1, so it is 4 to the power k. Okay. So all we are able to do is that we are able to bound the search tree of multi-way cut algorithm by 4 to the power k and not 4 to the power k square. Still, we need to bound lot of work at each node. Okay. This does not imply that we have a 4 to the power k algorithm, but it immediately implies that we have achieved a better algorithm. Why? Because what is your algorithm doing? Algorithm enumerates important cuts, enumerates important cuts and enumerate important cuts and run the algorithm recursively. Okay. So at this point of time, at each node, the running time of the algorithm I can only say that it is say 4 to the power k times k to the power big of 1 n plus m. right? Because that much amount of time to enumerate each important cuts and recursively go. And since there are number of nodes is upper bounded by 4 to the power k, so the running time of the algorithm will be 4 into 4, 16 to the power k, k to the power big O of 1 into n plus n. Okay, so this is the running time of the algorithm. But what we promised is an algorithm with running time 4 to the power k, k to the power big O of 1 and into n plus n. And to achieve this, it is a bit more complicated, and I'll refer you to the book for this, but let me give you some idea how we achieve these kind of running time. Look at the number of leaves. Number of leaves is 4 to the power k. Now look at work at any node. Work at any node, work at any node, if we could show that the work is proportional to the number of leaves, then we are happy. But the problem is work may not be proportional to the number of leaves, because you do not only enumerate important cuts which you need for your algorithm, but you actually enumerate a family of sets, and from there you filter out important cuts. So there are some subtlety that we need to handle, but we can handle those subtlety and leading into 4 to the power k algorithm. So ultimately we will show that the amount of work everybody does is proportional to the total number of edges in this graph, in this tree, which is like 4 to the power k times k, roughly number of edges. Okay, I think that leads us to the following algorithm. If every vertex is t in a different component, then we are done. Let t in t be a vertex that is not separated from every t minus t. You branch on a choice of an important cut, you delete g minus a, decrease the parameter, go to step 1. So this is the algorithm we had in the beginning also, but we first gave an algorithm with 4 to the power k square dependence on k, then 16 to the power k, and I gave you just very briefly, I would say nothing like that you can get from 16 to the power k, 4 power k, with more refined and measured analysis of the whole algorithm, but I leave that for you to make work out. Okay, and there are some other simple application of important cut which I will not talk, but like you can look into these slides. I will just leave it there because they are very useful and very good. Like for example, you can show that you fixed a node t and look at the degree, look at the number of edges which are incident to a vertex t. You can say how many edges are a part of minimal st cut of size at most k incident to t. You can show that that is also some function of k, in fact k into 4 to the power k, again using an application of important cuts, but I will leave that there. And with that we will end this lecture, and we will try to see another application of important cuts in directed feedback vertex set and why it cannot be applied to other cases of multi-way cut or like other generalization of multi-way cut such as multi-cut in the next couple of lectures or maybe at most one lecture. So thank you.